Look around you. You see stars, planets, and galaxies. You and I are part of it all. This may have all started from something incredibly small. This is not a story about a simple explosion. It's about the void itself. It is not what we think. The entire universe might have come from nothing. This sounds like the ultimate puzzle. How can a universe with billions of galaxies appear from nothing? For thousands of years, this question belonged to thinkers and writers. Our gut feeling tells us you can't get something for nothing. But when we ask physics, we get a surprising answer. The laws of nature suggest a universe from nothing is possible. It might have been unavoidable. This journey goes to the edge of reality. Cause and effect become blurry there. Space and time are a storm of possibilities. We must redefine the word nothing. In physics, nothing is not an empty void. It is a place full of potential. It is a sea of energy where reality can be born. This is the scientific story of our origin. First, let's define nothing. Most of us think of nothing as a perfect void. It is completely black and silent. There is no space, time, or matter. No rules exist. If the universe came from that, it would be a true miracle. But physics sees it differently. In quantum physics, a truly empty void does not exist. What we call empty space is actually the quantum vacuum. Imagine a calm ocean. From far away, it looks still. It looks like nothing is happening. But up close, you would see chaos. The quantum vacuum is like that. It is the lowest energy state of the universe. It is what's left when you remove every particle. You are left with what seems like empty space. But on the quantum level, this emptiness is full of energy. This energy is called vacuum energy. It is a result of the Heisenberg uncertainty principle. This principle says you can't know certain things about a particle at once. For instance, you can't know its exact position and its exact speed. There is always a trade-off. This uncertainty also applies to energy and time. For very short moments, the energy in any spot can change wildly. This means the vacuum is never truly at zero energy. It is always borrowing small bits of energy. From these energy changes, virtual particles are born. They pop into existence with their antimatter twins. Then, they instantly collide and vanish. This is not science fiction. This quantum foam is a basic part of our reality. We know this is not just a theory. We can measure its effects. The best proof is the Casimir effect. Take two metal plates. Place them very close together in a vacuum. A strange force pushes them together. That force is the vacuum itself. The small gap limits the virtual particles that can appear there. Outside the plates, the full quantum foam is active. This creates a pressure difference. That pressure pushes the plates together. The Casimir effect is real proof that empty space is a physical thing. This new definition is key to our mystery. The universe did not come from an absolute nothing. It likely came from a physicist's nothing. This quantum vacuum held the potential for everything. So the question changes. It is no longer, how did we get something from nothing? It is now, how did the quantum vacuum erupt into a universe? Our nothing is a busy quantum vacuum. How did it create everything? The answer is in those virtual particles. The vacuum's energy is like a bank account. It must always balance to zero. The uncertainty principle allows a kind of cosmic loan. For a moment, a fluctuation can borrow energy. It creates a pair of virtual particles. As long as the loan is paid back quickly, the books are balanced. This happens all the time, everywhere. Normally, this is all very small. But what if a fluctuation was so big, it changed the rules? Physicists like Stephen Hawking explored a big idea. What if the total energy of the universe is zero? This sounds impossible. How can a universe full of stars add up to zero? The answer is a cosmic balancing act. All the matter and energy we see is positive energy. But there is another kind, the energy of gravity. Gravity is an attractive force. To pull two objects apart, you need to add energy. So, objects bound by gravity have negative energy. The idea is simple. The positive energy of all the stuff is perfectly canceled out by the negative energy of gravity. The grand total is zero. If that is true, it is amazing. It means the universe is the ultimate free lunch. A quantum fluctuation could create a universe. It would not break any energy rules. The net cost is zero. Positive energy was created with the negative energy of gravity. This opens up a stunning possibility. A whole universe could appear from the quantum vacuum. It would be like a virtual particle, but instead of vanishing, it would be a bubble of space-time that could grow. Physicist Alexander Vilenkin proposed a model. A universe could have tunneled into existence from nothing. In quantum mechanics, tunneling is when a particle passes through a barrier it shouldn't. Vilenkin suggested that a state of pure nothing is unstable. It will naturally decay into something. That something would be a tiny, hot, dense universe ready to expand. So the laws of physics might be the only cause needed. As Stephen Hawking said, spontaneous creation is the reason there is something rather than nothing. It is not necessary to invoke God. A universe could be a natural random event. In the quantum world, it might have been guaranteed to happen. So we have a possible cause, a quantum fluctuation. And we have a condition, a zero-energy universe. Let's look at the event itself. A tiny bubble of potential became our universe. This is the story of the Big Bang. It was not an explosion in space. It was the explosion of space itself. The theory of cosmic inflation connects these ideas. It was proposed by Alan Guth. In the first fraction of a second, the universe expanded incredibly fast. This was a hyper-expansion. It was driven by the energy of the vacuum. In that instant, the universe doubled in size at least 90 times. It grew from smaller than a proton to the size of a grapefruit. This expansion was faster than light. That might sound like it breaks Einstein's rules, but space itself was stretching. Think of two dots on a balloon. When you blow it up, the dots move apart. The distance between them grows very fast. This inflation is very important. First, it took that tiny bubble of spacetime and blew it up. It locked in its existence. It was the bang the universe needed to start. Second, it explains why our universe is so uniform. The oldest light we see has the same temperature everywhere. This was a big puzzle before inflation. How could separate regions have the same temperature? Inflation solves it. Before the expansion, the whole universe was a tiny, connected area. It had time to even out its temperature. Inflation then stretched that smooth patch to a huge size. Third, inflation solves the flatness problem. Our universe seems to be geometrically flat. It is perfectly balanced. For it to be this flat today, it must have started almost perfectly flat. Inflation does this automatically. Any curve would have been stretched out and flattened. But the most amazing part is this. Inflation took tiny, random quantum jitters. It stretched them to a huge size. Those tiny fluctuations became the seeds for everything. The slightly denser spots gathered matter. The less dense spots became the great empty voids of space. We can actually see this. We can map the cosmic microwave background. We see small temperature changes. Those hot and cold spots are the old signs of those quantum fluctuations. They were blown up by inflation. They are the blueprints for the galaxies we see today. Every galaxy, star, and planet exists because of a random quantum tremble. Inflation stopped. The universe was then a hot, dense soup of pure energy. This energy turned into a storm of elementary particles. Quarks, electrons, and photons appeared. The stage was set. In those first moments, something important happened. We are still not sure why. A small imbalance occurred. For every billion antimatter particles, there was one extra matter particle. Matter and antimatter met and destroyed each other. That tiny bit of extra matter was all that was left. Everything we see is made of those leftovers. Within minutes, the universe cooled down. Protons and neutrons formed. They then fused into the first atomic nuclei. This was mostly hydrogen and helium. For the next 380,000 years, the universe was a glowing fog. Light could not travel far. After 380,000 years, a key event happened. It's called recombination. The universe cooled enough for atoms to form. Suddenly, the fog cleared. Light was free to travel across space. This first light is what we now see as the cosmic microwave background. After this, the universe entered the cosmic dark ages. It was full of gas, but there were no stars. But gravity was working. It was guided by the quantum fluctuations. An invisible thing called dark matter also helped. Denser gas regions began to pull in more material. About 150 to 200 million years after the Big Bang, the first stars were born. The dark ages ended. These first stars were giants. They were much bigger than our sun. They burned hot and died fast. They exploded as supernova. Those explosions changed everything. They created heavier elements like carbon, oxygen, and iron. These are needed for life. They spread these elements across space. This material formed new stars and galaxies. The James Webb Space Telescope is now showing us this early time. It sees structured galaxies forming earlier than we thought. Over billions of years, gravity built galaxies. It built clusters and superclusters. It all followed the blueprint from a quantum fluctuation. About 9 billion years after the Big Bang, our sun was born. The Earth formed around it. But there is one last twist. About 5 billion years ago, a mysterious force appeared. It is called dark energy. It seems to be part of space itself. It is making the universe expand faster. The universe is again being pushed apart by the energy of the vacuum. This force will decide its final fate. We started with a puzzle. How can we get something from nothing? But the puzzle fades when we look at the physics. The answer is that nothing is unstable. A perfect empty void may not be possible. The true state of reality is the quantum vacuum. It is a place full of potential. If the universe's total energy is zero, it could have just happened. A random quantum event could have created our universe. It did not need an outside trigger. Inflation took that tiny seed and blew it up. It created the universe we know. It also embedded the quantum seeds that grew into galaxies. The evidence for this story is all around us. We see it in the universe's expansion. We see it in the oldest elements. We see it in the afterglow of the Big Bang. So, did the universe need a creator? Our best theories say the laws of physics might be the only cause needed. Our universe could be the result of a natural, random process. We live in a universe that seems to have created itself. This is not a final fact, but it is the best story science can tell right now. It changes the question. The question is no longer, why is there something rather than nothing? Now we ask, why do we have these laws of physics? Why do the rules allow this to happen? That is a question for future discoveries. But the journey so far has shown us something amazing. We are made of stardust. We are the universe, now aware. We are living proof that nothing can become something, and that something can look back and wonder at its own existence. Did you enjoy this journey? Subscribe and join us. We will keep exploring the biggest questions in the universe. The universe has many mysteries. What is dark matter? Is there life on other planets? What cosmic mystery should we explore next? Let us know in the comments below. Thanks for watching.